This will be a walkthrough of the AQA GCSE Combined Science Physics 2023 Higher Tier Paper 2. Question 1. The Sun emits a continuous spectrum of electromagnetic waves. Figure 1 names some of the groups of waves in the electromagnetic spectrum. So in Figure 1, it's given us infrared, visible light, ultraviolet, and gamma rays. 1.1. Name groups A, B, and C in Figure 1. Well, electromagnetic spectrum is a continuous spectrum of waves, as it says, and this is in some sort of order. The order that you can have the electromagnetic spectrum, usually from left to right, is increasing frequency or increasing energy, and also decreasing wavelength. So what we need to do then is we need to remind ourselves of what will have the longest wavelength, because that would be at the far end, so what would be A, and then going towards the right hand side, what would have the second highest frequency or second shortest wavelength. So in our electromagnetic spectrum, our longest wavelength is radio waves, and then after radio waves it would be microwaves. Then we have our infrared, visible light, ultraviolet, and then just before gamma rays we have the most dangerous, which is X-rays and gamma. 1.2. Give one similarity and one difference between the properties of ultraviolet waves and gamma rays. Well, similarity first. Well, remember that they're all part of the electromagnetic spectrum. So they will travel at the same speed, no matter what part of the spectrum it is. And that speed is 300 million meters per second. So they all travel at the same speed. But we're looking for difference now. And differences, as we were mentioning before, will be the wavelength, frequency. So which one is going to have the highest frequency? It's going to be gamma rays. So gamma has higher frequency. And we could also say that gamma has a shorter wavelength. Figure 2 shows white light split into a spectrum of different colors by a glass prism. 1.3. Light changes direction when it enters the glass prism. What name is given to this process? Well, we've got light, which again is a wave. And right now it is in air. When it enters the glass prism, of course it's glass, these are different media. Now what can be different about the medium is the density. Now when the light enters a more or less dense medium, it can bend, change direction, speed up, slow down. And that process is known as refraction. Specifically, when it's dealing with light and it's split into different colors, that's known as dispersion. But in general, we should be writing the name of the process, and that is definitely refraction. Use the physics equation sheet to answer questions 1.4 and 1.5. 1.4. Write down the equation that links frequency, wavelength, and wave speed. So we either use the physics equation sheet or use our own recall. That will be wave speed is equal to frequency multiplied by wavelength. So if we're just using the abbreviations now, that would be V equals to F lambda. 1.5. The wave in the middle of the spectrum has a wavelength of 5 times 10 to the power minus 7 meters. The wave speed of light is 3 times 10 to the power 8. Calculate the frequency of the wave. So, using the equation, which you can just state it again. In the question, we're given the wavelength, 5 times 10 to the power minus 7. So we can state that first. And then we're given the wave speed, so 3 times 10 to the power 8. And then we need to find the frequency. So there's our first mark by plugging the numbers into the equation. We just rearrange it now. So that would actually then be 3 times 10 to the power 8 divided by 5 times 10 to the power minus 7. If we do that, we should get a value of 6 times 10 to the power 14 hertz. Question 2. A student investigated how the acceleration of a trolley is affected by the force acting on the trolley. Figure 3 shows some of the equipment used. So we have a trolley and a runway. Reading this first sentence again is how the acceleration of a trolley is affected by the force acting on the trolley. So this is going to give us an indication of what we might be measuring and what we might be changing. 2.1. Describe a method the student could use. Your answer should include any extra equipment needed. 6 marks. So this is related to a required practical on acceleration. So what we should be doing first is trying to state the variables. So independent variable, dependent variable, control variables. So what are we going to change in this experiment? Well, how the acceleration is affected by the force acting on a trolley. So how the force, when changed, affects the acceleration when we measure it. So we would need to mention some way of changing the force acting on the trolley. Well, one easy way that we can change the force acting on the trolley is causing there to be a change in the mass of the trolley. Now, changing the mass of the trolley is going to be difficult in terms of the structure of the trolley as we see it here. So we don't want to change anything about the trolley itself right now. But what we can do is we can add masses to the trolley. Now, one way you can add a mass to a trolley is by attaching a string to the trolley. And then at the end of your runway, you can put a pulley. And then at the end of the string, there will be masses that are attached. Now, when someone lets go of the masses, they're going to drop to the ground. That's going to pull the string down, and because the string is attached to the trolley, that will cause the trolley to move. If we were to add more masses, then that should mean then that the trolley should move even faster. So there's our extra pieces of equipment there: string, pulley, masses. So what we're doing then we're changing the force acting on the trolley that way. Now, for our dependent variable, what we're going to measure, well, we want to measure the acceleration. But we don't have a piece of equipment that will allow us to measure the acceleration. But we have calculations and equations that can help us to calculate the acceleration. Now the easy things that we can measure in an experiment will be the time and distance. So for us to measure the time, we can easily use a stopwatch. So what we could do is we could time how long it takes for the trolley to move down the runway. But for distance, we can measure using a ruler. But what we want to do though is we want to find out how quickly does the trolley move at a set distance. So one way in which we could do that is we could add markers to our runway, an ending and a start point. And then we start the stopwatch when it moves past the start point, and then stop the stopwatch when it reaches the end point. Now if we do that, seeing as we've got a distance and a time, what we're then able to calculate would be a speed or velocity. And if there will be a change in the speed, that will actually be the acceleration if we take that over time. Because our equation for acceleration is going to be the change in speed divided by time. So by doing these short calculations, we are then able to find the acceleration. But the dependent variable in the experiment would actually be the time for trolley to move down runway. And now our control variables, what are we going to keep the same here? Well, what could change the acceleration other than the force? Well, one thing could be the height of the runway. If we start changing the height of the runway, that can affect how quickly the trolley moves down the runway. So we definitely want to keep that the same. Remember that the mass of the trolley itself is something that we want to keep the same. But also the material that the runway is made from. Because remember that the runway is what the wheels of the trolley is going to move along. If we start making the runway smooth or start making the runway rough, that could cause the trolley to have a different speed as it moves down the runway. So we want to make sure that we keep that the same. So the height of runway and the surface material of the runway. Okay, so we're ready to describe our method now. And remember what we need to do first. We need to set up the trolley so it's ready to move. So what we want to do is attach a pulley to one end of the runway. Then attach the string to the trolley, and then that string will go on the end of the pulley. Then what we're going to do is we're going to attach a single mass to that trolley, to that string. So our trolley is set up now. Next thing you want to describe is what we're going to do on the runway. So marking the start and end points of the runway. But we have to use a ruler so we can measure that distance, because we don't want that to change. And then once we are ready to begin, what we can do is let go of the masses and then start the stopwatch when the trolley goes past the start point and stop it when it reaches the end point. We then need to talk about our calculations now. So calculation 1 would be to calculate the speed. we'll just use the abbreviations for that. And then acceleration using the next equation. And there's our answer for 6 marks, describing the method. Table 1 shows one set of results for a similar investigation. The resultant force in newtons is 1.2. The acceleration in meters per second squared is 1.6. 2.2. Which of Newton's laws predicts that the acceleration of the trolley is proportional to the resultant force on the trolley? Tick one box. Well, we've got to think about which of Newton's laws now is linked to acceleration and force. Well, the first thing that we can think about is an equation that's linking the two, and that is our force equals mass times acceleration equation. What it's telling us is that if we increase the force, acceleration will be increased by a certain amount, and vice versa. Which law is linked to this equation? That will be Newton's second law. (2.3) Determine the acceleration of the trolley when the resultant force is 3.6 newtons. Use table 1. So let's go back to table 1. The resultant force was 1.2 in that table. So 1.2 newtons is equal to 1.6 meters per second squared. But the question is now, force has changed to 3.6 newtons. What will the acceleration be? Well, what we can do is you can find out how much bigger is 3.6 newtons than 1.2. So what we need to do then is 3.6 divided by 1.2, and that will equal 3. So it's 3 times bigger. So if that force is 3 times bigger, then the acceleration should be 3 times bigger. So it'll be 1.6 multiplied by 3, and that will be 4.8 meters per second. Use the physics equation sheet to answer questions 2.4 and 2.5. Write down the equation that links acceleration, mass, and resultant force. Well, we just did that. That's Newton's second law equation, which is F equals m times a. (2.5) A resultant force of 0.42 newtons acts on a different trolley. The acceleration of the trolley is 1.2 meters per second. Calculate the mass of the trolley. So let's state the equation again. Plug our numbers in. 0.42 is our force. The acceleration is 1.2 meters per second. We don't know the mass, so we need to rearrange the equation now. So that will be 0.42 divided by 1.2, and that will equal our mass. So putting that in a calculator, our mass will be 0.35 kilograms. Question 3. A teacher used a ripple tank to demonstrate water waves. The teacher used a lamp to project the shadow of the water waves onto a screen below the ripple tank. 3.1. Figure 4 represents the shadow of the water wave seen on the screen. 1 millimeter on figure 4 represents 5 millimeters on the screen. Determine an accurate value for the wavelength of the waves on the screen. Give your answer in millimeters. Show how you work out your answer. Well, we're trying to find out the wavelength. This actually is also a question related to your required practical for waves, speed of waves. So remember that the wavelength is the distance between two peaks on a wave. So what we're really trying to find out then is the distance between the two waves. because each of these solid lines are the water waves. So really trying to find out the distance between them. Now, the key information that they've given us here is 1 millimeter on this figure represents 5 millimeters on the screen. So what that would require us to do now, it will require us to measure this distance between the two waves. Once we do that, this sentence is really just giving us a scale to reference. So if we were to measure it, and we're just going to use an estimate here, if the value of the gap between the two water waves, so our wavelength, was 8 millimeters, we would need to use the scale to find out what it would actually be. So if 1 millimeter would be equal to 5 millimeters on the screen, then if we've measured 8 millimeters, that would just then be 8 millimeters multiplied by 5, which would be 40 millimeters. So by using a scale and calculating, we'll be able to get our 2 marks. What we need to take into account, though, is what is the full distance that will be on our water waves. So that full distance, once you just measure it, that will give us a value of 113 millimeters. Now remember that you're measuring here, so there will be some leeway, some range of answers that you can get. So as long as you have done your calculation properly here, you are guaranteed to work out, to get 2 marks. The teacher adjusted the frequency of the waves produced in the ripple tank. The teacher measured the wavelength 5 times. Table 2 shows the results. So for each of the measurements, there's a wavelength given, except for measurement 4, where it's x, and the mean is calculated. 3.2. Calculate value x in table 2. So how did they obtain the value of 97 for the mean? Well, to find the mean, you add up the numbers for your measurements and divide it by how many there are. So what they would need to have done is 96 plus 99 plus 97 plus x plus 97, and then divide that by 5, and then that would equal 97. So what we should do to try and obtain our answer then is add up the 4 values that we know. So add 96 plus 99 plus 97 plus 97. And then that will be equal to whatever 97 times 5 is by excluding this x. So it'd really be 96 plus 99 plus 97 plus x plus 97 equals 97 multiplied by 5. So you add up the 4 values now, and then once you do that, you just take it away from whatever 97 times 5 is, and that will give you the value of x. So if you do that properly, you should come out with a value of 96, and that will be the missing value. 3.3. The teacher states that the results are very precise. Which of the following supports the statement made by the teacher? Tick one box. Well, precise means that the values that you get are very close to each other. That's different to the word accurate, because accurate means that your values are close to the target, the true value. So let's read them and see which description matches precise. First one, the mean value is very close to the true value. Well, that's what accurate means, as we said, so it can't be correct. The spread of the values about the mean is very small. Well, yes, this matches what precise means, because the values aren't too far away from each other, so the spread is very narrow. So that would be correct. The values are all given to the nearest millimeter. No, that's not helping us with what our precision means here. And the wavelength measurement was taken 5 times. That would improve the reliability of our results. So our correct answer is the second statement. 3.4. Describe the difference between longitudinal waves and transverse waves. So it's the definition of these two phrases now, longitudinal or transverse, which we need to recall right now. So when we think of longitudinal, we're thinking of the word parallel. When we see the word transverse, we should be thinking of the word perpendicular. And perpendicular means at right angles, which is 90 degrees. Now, what, in the case of longitudinal waves, is parallel? Well, it's going to be the vibrations are parallel. But what are they going to be parallel to? It's to the direction of energy transfer. And then for our transverse wave, we would just need to then replace that word parallel with perpendicular. So let's just write it all out again. I'm pressing perpendicular this time. Remember, what we have to do lastly is identify which of our descriptions is for a transverse wave and which of our descriptions is for a longitudinal wave. So we can just write on the side that in longitudinal waves and then in transverse waves. Question 4. A teacher demonstrated the motor effect. Figure 5 shows the equipment used. The equipment includes a permanent magnet. So here's our setup, circuit, with an open switch, a magnet, and within the magnet there is a copper rod which is set on a brass rail. 4.1. The copper rod remains stationary while the switch is open. Complete the sentence. The tendency for an object to remain stationary is called. So we're dealing with forces now, and if an object tends to remain stationary, tends to remain at rest, because that's what stationary means. This is linked to Newton's third law, and this actually is known as inertia. When the switch is closed, the copper rod accelerates. In which direction will the copper rod accelerate? Tick one box. Well, if the copper rod is accelerating, that means that it's moving. And if the copper rod is moving, it's because a force has been applied to it. So now if we're trying to identify the direction at which the force is acting, That means that we are dealing with the Fleming's left-hand rule. So we have to go back to our diagram to do that. The other way that we know that it's dealing with the left-hand rule is because it says that it's demonstrating the motor effect. So for our use of Fleming's left-hand rule, we need to remember what each of our fingers represent. So it's F, B, I. F is the force, and that's represented by our thumb. B is the magnetic field, and that's represented by our first finger. And I is the current, and that's represented by our middle finger. So how does it work now? Remember that we're trying to figure out the direction of the force. So we should then know the magnetic field, and we should know the current, and then they're all going to be at right angles to each other, so you can figure it out from there. So the magnetic field, how does it work? Magnetic field is always from north to south. So knowing that information now, we would have to place our first finger downwards from north to south. Our current direction. Well, in the case of the circuit now, we can see that the positive terminal here and the negative terminal must be there. So our current is going to move from negative to positive. But we have to view this circuit as if it was lying on a plane like so. Now, of course, that's quite difficult to do with the paper. So that's why they've put it at an angle here. So if it was actually laid out in 3D in front of us, the circuit would be laying down flat on the surface. So by that description and that understanding, the current actually would be moving towards us. So imagine that this arrow is drawn and it's facing you. So that would mean that our current finger, which is our middle finger, would need to be pointing directly towards us. Now, if you set out your left hand in that direction, your first finger pointing downwards and your middle finger pointing outwards towards you, your thumb, which is your biggest finger, should be facing towards the right. So that means that the force, and therefore the acceleration, will be in that direction. .3. Explain one way the teacher could increase the acceleration of the copper rod. So that means then causing the force to be greater. Because if the acceleration is going to be higher, that means that the force that is added to the copper rod has got to be greater too. So what is going to cause the force to increase from our circuit? What could we do? Well, one easy thing that we could do is we can change the magnet so it's stronger. The stronger the magnetic field, the greater the force that's applied to the rod, so it then should cause the acceleration to be greater. What else could we do though? Well, if you look carefully in the circuit, there is a variable resistor that is present. And what does the variable resistor allow you to do? It allows you to adjust the resistance, decrease it and increase it. Now remember that the magnetic field will be provided by the magnet, and we've already discussed changing the magnet, so making it stronger. But the other thing that's involved in our left-hand rule would be the current. So it could be adjusting the current. Then which way are we going to adjust it? Well, again, we want the magnetic field to be stronger. We want the force that's applied to the rod to be stronger. So by increasing the current, that would increase the force applied to the rod. How would we change that in the circuit? Well, the easiest way would be to decrease the resistance. So we can say any of those two methods then. So we could say use a stronger magnet. And what will that do? That will increase the force applied to the copper rod. 4.4. The magnet used in a demonstration was a permanent magnet. Figure 6 shows an iron bar and a permanent magnet. Describe how the permanent magnet could be used to test if the iron bar is also a permanent magnet. Well, if we look at our permanent magnet now, it's got the south pole identified and the north pole identified. What do we know about how magnets work? You should know that like poles repel, and opposite poles attract. So, with that information then, what could we do? We could take our permanent magnet, move it closer to the iron bar. Now, if it was a permanent magnet, then it would have its own north pole and south pole. What should we expect if we bring the permanent magnet closer to the iron bar and it actually did behave like a permanent magnet and its south pole was facing the permanent magnet's south pole? Well, it would move away, and that's the repulsion. So that would be our way to definitely tell that our iron bar is a permanent magnet. So move the south pole of the permanent magnet towards the iron bar, and then the bar would be a permanent magnet if there is repulsion. .5. Figure 7 shows a magnetic compass used by walkers. Explain how a magnetic compass provides evidence that the Earth has a magnetic field. Well, if we look carefully at this compass, the compass has a needle. The needle is facing the north pole on the compass. What does that mean? That means that the compass needle is attracted to something. Now, if you make sure that there is no magnet that is near the compass, it will always be facing in that north pole direction. So that means that it's attracted to something that is existing on Earth. And that's the magnetic field of the Earth. If you take a magnet near the compass, then it will start to move the needle towards wherever that magnet is. You take the magnet away, and the compass needle will go back to north. So there's your evidence. The compass needle is always facing north, provided there's no magnet next to it. But we won't need to include that. So why is it always facing north? Because it's attracted and aligning with the magnetic field of the Earth.